Hi everyone, my name is Ursula and I'm going to give you a tour of my lab today. My friend Shauna, who also works in the lab, is going to film, so I'm going to slip on my mask and head to the lab. Okay, so welcome everybody to Becky Alexander's laboratory. Becky Alexander is a professor in the Atmospheric Sciences Department and I work with her as her graduate student. And most of what I work on involves analyzing ice core samples for sulfate. So ice cores are long tubes of ice that are taken from really cold, snowy places like Antarctica and Greenland. And when I have these ice cores, I can measure the concentrations and the different isotopes of sulfur in the sulfate, which tells us a lot about how the atmosphere works. So the first step of this process is I take my ice core sample and I'm going to pour it through a funnel into a resin. And the resin is at the bottom of this column. And so what happens is when I pour the ice core sample into this funnel, the resin captures the sulfate compounds, the ions, and it holds onto them so that I can isolate the sulfate out of the ice core sample. Because in this entire bottle of water, which used to be an ice core, now it's melted, all I actually want to analyze is the sulfate. So like I said, I'm analyzing sulfate, and I drew a picture of sulfate here for you. Sulfate is an ion, which means that it has a negative electrical charge that's composed of one sulfur atom, which is this S, and 4 oxygen atoms that are all bonded to the sulfur atom. And so these ions are in ice cores, and they're also in the atmosphere. And by analyzing the sulfate ions in the ice cores, I can learn a lot about the atmosphere, because sulfate is very important to cloud formation and reflecting sunlight from the atmosphere. So once the ice core has gone through the funnel and passed through the resin, I can then pass some hydrochloric acid through the resin. The hydrochloric acid will kick the sulfate ions off of the resin, and that will release the sulfate ions into a new solution that I can then capture. And the whole point of this process is to concentrate the sulfate ions so that rather than being in a 2-liter sample of ice core, they're in a 2 milliliter sample of ice core. So I'll show you using the hydrochloric acid really quickly. Right now, this is called a pipette. And what I'm doing is I'm using this pipette to suck up a known volume of hydrochloric acid. So this is 1 milliliter of hydrochloric acid, and I'm putting that into the resin to release the sulfate ions. And hydrochloric acid is very acidic, so if you've ever gotten lemon juice on your hands, you know how it stings a little bit? Hydrochloric acid has that same property where if I were to spill that on my hand, it would sting a little bit. This is pretty diluted, so I don't have to wear gloves, but with very concentrated hydrochloric acid, you do have to wear gloves. So after I put 1 milliliter hydrochloric acid through the resin, I'll put 1 milliliter of water through the resin just to rinse it. So I'll show you here. Okay, so now all of the sulfate that used to be in an ice core sample that filled this whole bottle is in this tiny little vial. So I've really concentrated the sulfate into this little small amount of water. After that, what I'm going to do is I added barium chloride, which will help make the sulfate form into a salt that kind of precipitates or becomes particles in the water. And I'll put this in a boiling beaker of water, and I'll evaporate off some of the water. And now we're going to let this boil for 2 hours. Okay, so this is a vacuum pump, and when I turn this on, it sucks air out of this chamber, and that pulls any water that I put into this funnel down through that pipe. And the reason that I'm going to do that is because I'm going to take the sample that has the sulfate and the salt form, so it's those solid salt crystals, and I'm going to pour it into this funnel, and then it's going to pass through one of these tiny, tiny filters. And the reason that we do that is this filter will let the water pass through, but it will capture all of the sulfate salt. And then once I do that, I will have my entire sulfate sample that used to be in that giant ice core bottle all captured onto a tiny white filter. So I'm sucking up the sample using the pipette. and then I'm putting it into the funnel, and then all of the salt that is in this sample will get captured on that filter. Okay, so now I'm taking apart this funnel so that I can get the tiny white filter that I talked about. Here it is. Pick it out of the funnel and put it into a tin capsule in this sample tray. So now I'm taking this tray full of samples and I'm putting it inside what's called a rotovap, because it's a rotating evaporator. It rotates like this, and then it causes any of the water that's still on the filter to be evaporated off. And there we go. Okay, so while these samples are in the rotovap, I want to show you this ion chromatograph really quickly. So the ion chromatograph is a machine that we use to measure the concentration of sulfate in an ice core sample. So to test and make sure that the resin was capturing all of the sulfate ions, the first thing that we did was measure the concentration or the expected amount of sulfate that we would get with the resin in this ion chromatograph. So that's what this tool is used for. Welcome to Isolab. This is the other laboratory that I work in, and it's in the Earth Sciences building. And there are many different machines in this laboratory. And as you can see, it's pretty loud in here most of the time because there are so many different machines running. So first on this back wall, we have a bunch of different compressed gases. These gases help pressurize the machines to make sure that we're able to analyze our samples. This is liquid nitrogen, which keeps things very, very cold. Liquid nitrogen is a temperature of negative 196 degrees Celsius. So you don't want to touch it, it's very cold. These are tanks of nitrogen, carbon dioxide, oxygen, and helium. And these are all used again in the machines to keep them pressurized and help analyze different quantities and different kinds of gases. This is a mass spectrometer. We've nicknamed it Boris. This is another mass spectrometer that we've nicknamed Lorax. And finally, this is a mass spectrometer that I use the most. Its name is Shrek. A lot of them have silly names just because professors think that that would be fun. And I use this mass spectrometer to analyze different isotopes, which is different weights of sulfur in the sulfate anions. And the reason that I analyze isotopes of sulfate is because that can help us know where the sulfate is coming from in the atmosphere. Is it coming from humans burning fossil fuels? Is it coming from sea salt in the ocean? Is it coming from forest fires? There are a bunch of different sources of sulfate. And if we measure the isotopes using this mass spectrometer, we can know where the sulfate is coming from. So the first thing that we do is I put those samples that I showed you, like that little white filter paper in the tin capsule. I put that in this sample tray, and I can actually unscrew it. So this is the sample tray, and I'll put lots of individual samples into these holes. And then I'll close this tray. And then what happens is the samples get dropped into a column of quartz tips. And that column is very, very hot. It's 1,050 degrees Celsius. So you also don't want to touch that. It's like a really hot oven, about twice as hot as what you're baking your pizza in. And that will combust or burn the sulfate to form SO2 gas. This SO2 gas will flow through the mass spectrometer system and through these pipes that you can see. And then what happens is this wire gets lowered into this tank. And this tank usually is full of liquid nitrogen. As you can see, there's still a little bit left in there. And the reason that we have it flow into the wire that goes into the liquid nitrogen is because that will freeze the SO2 gas, which allows it to concentrate into one portion of the wire. And then after that, the wire is raised, so the gas becomes no longer frozen, and it flows through the wire and goes to the plasma. So you can't see the plasma, but it's in here. And the plasma is like a really, really, really hot flame, and that causes the SO2 gas to break apart. And that will flow through a tube here And then it gets to, this is a big magnet, like a huge magnet, very powerful. And with the magnet will cause the flow of the gas to change direction. And that can tell you how heavy the gas is when it hits the other wall. So the gas flows through, gets bent by the magnet, and then hits a little cup over here, and then you can tell how heavy it is. And that's how we measure the gases in the stable isotope mass spectrometer. Okay, so now that I've shown you my part of the lab and what I work on, I thought it might be fun to introduce everybody to Andy.
Hello, I work in the Isolab as a technician and manager, and I do almost anything in here. I'm fixing a pump right here that needs new seals put in it. I purify carbon dioxide using liquid nitrogen. This particular line takes carbonate that may have come from a soil or a rock somewhere, and I drop it into a hot phosphoric acid bath that is like the volcano that you may have made, where you'd put baking soda on vinegar, except this is soil carbonate in phosphoric acid, and it turns into CO2, and I purify the CO2 so that it can go be analyzed on an instrument that's very much what like Ursula just showed you.
Is that what ethanol looks like when it's like frozen?
When it's nearly frozen, yeah.
Why do you do that?
Because I want to freeze water. And so this is about minus 100 Celsius. Minus 110, 120. Ooh, 130, too cold, too cold.
And what water are you freezing with it?
So the volcano reaction makes CO2 and water. And we want to separate the CO2 from the water. So we freeze the water with this, and we freeze the CO2 with liquid nitrogen.
Oh, because water will freeze at this temperature, but CO2 won't.
We'll just go right through, yeah.
Cool.
Yeah.
Very cool. Whoa. Okay, so will you explain what's happening? Like the CO2 plus water is like going in and out of these vessels?
Right, okay, so right now it's just pumping down, but as soon as I drop the carbonate, it starts reacting and is making CO2 and water. The water, it's under vacuum, so the water is freezing here and the CO2 is moving over here and freezing in here. We give that 10 minutes. And then we want to clean the CO2 even more, so we put it into a helium stream, thaw it out here. It moves through a custom GC column to separate out contaminants. And then these are up at that point, and if there's any water remaining, it freezes in here. The CO2 freezes here in the helium stream. The rest of the helium is leaving into the room, just like Shrek.
Okay.
And then when that's done, we pump all the helium away, lower these, freeze this tube, and let the CO2 move into the glass tube, and then we flame seal it in here.
Oh.
And now we have purified CO2.
So what ends up happening is you have all the carbonate in the white powder, and it ends up as CO2 in this glass tube.
Yeah.
Cool.
Hi everyone, my name is Shauna, and I'm a recent undergraduate at the University of Washington, and I work in this lab, and I work on multiple projects, and one of the projects I've been working on is measuring water isotopes. So this is a water isotope analyzer. So these are ice core samples. As you can see, they're little melted ice, basically, from ice cores, which we drill from Greenland and Antarctica. So what you see here, this is 3,000 meters below the ground. And so we put this on here, and then this analyzer measures its isotopes, its oxygen isotopes. So here we have this needle. So what it does is it takes the samples from the little vials, the little water in these vials, and it sucks it up, and then it goes through the analyzer and measures the isotopes.
Very cool. And I like your mask, Shauna.
Thank you.